what you did? Yeah, good. I moved that xy over, and I think it's a Bernoulli dE. I think I'm going to let u equal y to the 1 minus n, and what is the n?
1/2.
A 1/2, right. So 1 minus a 1/2, okay. So I think u equals y to the 1/2. So then du dx is 1/2 y to the negative 1/2 dy dx. You guys okay? This is a Bernoulli. I'm approaching it with this Bernoulli technique here. So now remember what I do? I like to multiply this y prime by what I think it needs. I think I want to multiply by 1/2 y to the negative 1/2. So it's 1/2 y to the negative 1/2 times this y prime minus x times 1/2 y to the negative 1/2 times y equals the square root of y here times 1/2 y to the negative 1/2. I multiplied everybody by what I think it needs. That turns this into du dx. That was my whole point in a way. And then over here, things get a little cleaner perhaps. I get this, I get this 1/2 x. What about this? When I multiply that together, it's a y to the 1/2. What's y to the 1/2? U. That's how that always works. That's how that always kind of works. Over on the other side, the y to the 1/2 and the y to the negative 1/2 cancel, and I'm left with the number 1/2. Okay, so now I got a linear first order dE. The variable is u, and it's good to go. I should do the integrating factor method. I'm a little worried this might not work out. We'll see what happens here. The integrating factor is a little funny. It's e to the integral of negative half an x. Well, that's e to the, what is that, x squared over 4? Yeah, negative x squared over 4. Okay, that's my integrating factor, I guess. It doesn't simplify, there's no log there or anything, so this time that's my integrating factor. What will I do? I think I'll multiply through by that. I'll multiply through by that. Okay, yeah, here's the problem. Damn it. After I multiply through by that, my right-hand side becomes the derivative of the integrating factor times u, and the other side becomes 1/2 times e to the negative x squared over 4. And do you remember the next step, you guys? Integrate. Integrate this is nothing. It pops right out. But now I think I've hit a wall. I'm sorry, you guys. I want to integrate this, and I can't.
It's easier if you forget the x's in the numerator and put it in the denominator instead.
It's easier, but wronger. But more wrong. So I was probably smart not to trust him. Because I've got myself, I think I did everything right, and I do. I have an unsolvable, I can't integrate this. We could talk about that if you want to have a big discussion about that, but what would make this a nice integral would be a nice x out here. Then you could let u equal the exponent. Du would kill that x. See, then it's a good u substitution problem. Without that x there, I am flat stuck. I cannot integrate an e to the x squared. It's an unintegratable function. There's a lot of functions can't be integrated. So I'm going to stop. I was trying to get y so I could predict the actual y value, right? I wanted to predict the actual y value, and we could compare it to these guys. But anyway, I can't solve it. So, you write that on your test, give you full credit. All right. Anyway, yeah, I'm speculate on that. You guys got any other questions or concerns or worries? Well, I might do this then. Yeah, listen, I'm not going to do much, but I'm going to do something. I'm going to hand you this piece of paper. This is our test is tomorrow. It's on chapter 1 and 2. I guess Monday we'll dive into chapter 3. By the way, according to the plan or the calendar, I think I spend about 3 days on chapter 3. I think we take a test next Thursday on chapter 3. Although chapter 3 is word problems, so we might have a take-home piece. Maybe that'll be due over the weekend. Maybe we'll have, but the in-class piece we'll try to get done Thursday, maybe next week. But anyway, it'll go quick. It's just a couple sections of chapter 3. But I want to show, sort of, just ease into it right now for 15 minutes. So when I do start chapter 3, I hand you this piece of paper. And I'll hand it to you now. And I want to talk about, I mean, it's sort of like a place for you to write notes, but if you prefer your notes, you don't really have to use this as notes. But here's these word problems are this. They start off as these English sentences. So I'm just sort of easing into chapter 3 here. I'm not going to do too much, but I want to show you a couple cool things. There's that first sentence there. That first sentence says, it's an English sentence, and I want to write it as a math sentence. Watch. It says, the rate at which a population changes over time is directly proportional to the population at any time. Okay, that's an English sentence. I want to write it as a math sentence. Did you hear what it said? It said, the rate at which a population changes over time. Good job. The rate at which a population changes over time is the derivative of that population over time, yes. And then it says it is, do you know how to write is? Good job. Right? That rate is proportional to, directly proportional to the population at any time. So when something is proportional to something, directly proportional, you introduce a proportionality constant k. So it is directly proportional to P, is what it said. It says it's proportional to the population at any time, which is just P, the population at any time. And so then this K is some proportionality constant. And that English sentence, we call that maybe a model. Things act like that. Things grow according to that. And this is the DE, that English, here's the math sentence, that is that English sentence. This is the math sentence. And it's a differential equation. And you can solve it. I can solve it. You can solve it. We can solve it. Let's just solve it. I would separate and integrate. I would treat the K like a constant. I leave the K there. I would do dP over P is K dt. Pretty simple one. I think we've already done one like this when we were working on some homework. I would integrate both sides. When you integrate this, you get the ln of P. When you integrate this, you get KT plus C. You guys okay with that? Pretty basic one here. And then you E both sides. When you E both sides, you get P, the population, is e to the KT plus C, but you've seen us deal with that a few times now. We call that C e to the KT, don't we? You guys okay with that? Everybody all right? Pretty cool, pretty basic. That's awesome. And so then this is our classic model for population growth and decay. Population growth and decay. I guess if the population gets some kind of disease, they could all be dying out. So this population could be growing or decaying, I suppose. By the way, that growth or decay sort of depends on the value of K. If it's positive, it's growth. If it's negative, it's decreasing decay. But, you know, this is just classic exponential growth and decay. I mean, I teach this to my college algebra students. We talk about this. Money earning interest, compounded continuously, follows this model. Radioactive substances decay following this model. I mean, I wrote it up using the word population, but the truth is it could be, this population doesn't have to be a population. It could be money, or it could be radioactive substances, but it follows this model. And this is a very basic model. You know, like I said, I teach my college algebra students this, but they don't see where it comes from. They don't know it came from a DE, and they don't know it came from that English sentence. You know? But it's cool. I like that. Now, the truth is, what happens in our problem, once we start doing word problems, and I don't know if I'll really do one with you today, but we kind of, then it turns into, when we start doing some actual word problems involving this, we end up just kind of working with this. I mean, we've done the DE, we've done the calculus, and so our word problems end up working with this, and they get very algebraic. I mean, there is no calculus or DE. It's kind of been done here, and now we get these algebraic word problems that aren't too hard, okay? They're not too difficult. Let's look at the next sentence, number 2, because so I'm not really doing a word problem yet. I'll wait till Monday on that. But let's look at the next sentence. The next sentence is very famous. It's called Newton's Law of Cooling. Again, I made up these notes partly because I didn't want to write the sentence again. But the sentence says, the rate at which the temperature of a body changes over time is directly proportional to the difference in the temperature and the temperature of the surrounding medium at any time. So that's the sentence in English. Can we write that in math? The rate at which the temperature changes over time. So I'm using capital T for temperature, and then I'm using little t for time. And I think that's so far that's what you write. The rate at which the temperature changes with respect to time is, and again now I think it says it is directly proportional to, so I need a K again, it's directly proportional. This time it's directly proportional to the temperature of the body, the difference in the temperature of the body and the temperature of the surrounding medium. So that would be, the difference would be the temperature of the body subtracting the temperature of the surrounding medium. So these are the variables. Temperature and time are the variables. But that M, we're going to treat that M as a constant. And by the way, of course, the K is a constant, of course. But we're going to treat that M as a constant. And it's the temperature of the surrounding medium. It's the temperature of the environment I'm in, you know. And I do want to treat it like a constant. But there are more advanced problems, listen you guys, more advanced DEs where maybe that M is not a constant. And then that makes it a more complicated differential equation, and maybe, I mean, we can do something like that later. But for today, the temperature of the surrounding medium is just a constant temperature. Hey, do you think we could solve this DE? I think we could. This one, I saw this in your homework. Oh, in your homework, they called this M. They called it T subscript M. I kind of like using M instead. But they had this in your homework as like a DE to solve. Maybe you've already done it. What would you do? Would you do the
multiply through?
Okay, you could. I think you actually could divide, and you could. I think the easy way would be to separate and integrate, a lot like this one. You kind of keep this together and divide, and it'd be the easiest way to do it. The truth is, I want to try the other method for fun here. I think I want to, and that's what you sort of said. You said multiply the K through there, and then I'm going to move it to the other side. Okay, I didn't lose you, did I?
KM would act as like a constant.
It is a constant. You're right. You're right. but I distributed the k through there, and then I moved the kt over to this side. I'm going to do the integrating factor method, even though I said the other method's easier, just for fun, just to do something different. What would be the integrating factor? E to the integral of negative k with respect to t. What is that? E.
Negative e to, what do you mean?
Well, it's e to the negative k t. That's the integrating factor.
Wouldn't it spit out a negative in front of you?
Well, you're over spitting out. You're sort of spitting out an extra. No, I mean there's the negative it spits out, and then I'm not doing any u substitution, so no, it's not spitting out another. Right. Yeah. I'm just integrating with respect to t. Yes, Zachary?
My hand was raised, so I wouldn't ask.
Oh, okay. And so now I got this e to the negative kt, and I multiply through by it. After I multiply through by it, the left-hand side becomes the derivative with respect to t of e to the negative kt times capital T equals negative km e to the negative kt. How you guys doing? Multiply through by my integrating factor. Now I integrate. When I integrate both sides, I'm going to drop down here. This comes out, e to the negative kt times capital T. Okay, you're right. All that's a constant. I'm integrating my e function. Integrating my e function is just himself, but it does spit out. You do a u substitution. I think it spits out a 1 over k, a negative 1 over k. If it spits out a negative 1 over k, it's going to kill that negative k. And so I'm going to be left with just an m in front of this, plus c. One more move. Divide by him, or multiply by e to the positive kt. The answer then is t equals m plus c e to the kt. I don't know if I talked too fast there or lost you. You should be able to handle that. But my point was, we're done. And a lot of times when I read these temperature word problems, I don't have to do the DE again. If m is constant, we've solved the DE when m is constant, and this is the model for Newton's law of cooling when m is constant. So you can read a word problem and start filling stuff in here and work with this and never do calculus. You with me? We've done the calculus, we've sort of done the proof. Now when we read a word problem, we tend to just use this model. This is called the model for Newton's law of cooling. Real similar, by the way, to that guy. Just has that added m in front of it. Did you do any of these problems in Cal 2 maybe? I mean, in Cal 2 when you open, I mean that was a little while ago, but at the very beginning of Cal 2 there is that little chapter on DE, and you could have done population word problems, or there's actually just 2 or 3 of these in there. I don't know. So did you do them?
Yeah, radioactive decay, population, and block corn.
You did those?
Yes.
Yeah. Good.
I like using the integrating factor method, though. That was unique.
Well, right. Okay.
It just gives us more ways to do it.
Right. Yeah, you could have separated and integrated. Right. That's true. Back in that, you didn't learn the integrating factor method really back then. Right. Yeah. Okay. Good. So we'll do more with these. We'll also do another very cool word problem that's at the bottom of the page. But I'm not going to do that today. In fact, I may not do much more at all today. I just wanted to get you thinking about some word problems for next week. The truth is, you could almost jump into 3-1 with these 2 ideas at the beginning of 3-1 and do a little homework this weekend if you felt like it, just to get ahead of the game a little bit. But we'll quit. Let's quit today, I guess. And I'll see you tomorrow at 8 o'clock, and we'll take a test.